So, ellipses. Last time we talked a fair amount about parabolas. Hopefully you all went out and bought a paraboloid reflector shield to cook your food in case the apocalypse comes. It's a fantastic little tool. But now today we're going to talk about ellipses. And again, we said that circles and ellipses are really all part of the ellipse. They're both part of the ellipse category. Obviously ellipses, but circles as well, as we'll kind of see here. Okay. So I said that each one of these conic sections, if you will, can be described by some kind of geometric property. Okay. For the parabola, remember the parabola, there was a directrix and a point called the focus. And the parabola was the collection of all points equidistant from those two. For the ellipse, it's kind of interesting. What you do is basically you start with two focuses. We call those foci, by the way. Okay, and essentially, it is an ellipse is the set of all points such that the sum of the distances from the two foci is a constant. Okay, so like this distance right here, d1, and this distance right here, d2, like d1 plus d2 is always some constant. Okay, so there's a way that we can visualize that we'll see on the next slide, but it kind of shows you how you might draw an ellipse using like a couple of thumbtacks and a string. Does that make sense? So basically d1 plus d2 just has to be a constant. Okay. The line through the foci intersects the ellipse at 2 points that we call the vertices. So if I were to draw the line through the two foci, I get a couple of points here and here that are called the vertices. Okay. But every other point on the ellipse is determined by this property that the sum of those distances from the foci to the point is the same number all the time. Whatever that number is, could be 5, 7, whatever. Okay? It's just going to affect the size of the ellipse itself. Okay. Okay, any questions on that geometric definition? Any questions? Okay. Moving on. So the chord joining the vertices, remember the vertices are the things on the end here. Like if I draw the line through the foci, I get the so-called vertices of this. The chord joining the vertices is called the major axis. Okay, so the major axis is the chord that actually joins those two vertices. Then if you draw if you take the midpoint of the major axis, that is the center of the ellipse. And we actually give coordinates to that, h comma k, all right, which we're going to reference later on. Okay, and then what you do is you draw the perpendicular to the major axis through the center. And that gives you a couple of other points that are important, okay? They're not called the vertices, but the axis itself that consists of this chord joining those two things, that is called the minor axis. Okay, so the big key is that's a right angle right there. And so we're just specifying various things that happen to be, like distinctives of the foci of the ellipse, like the foci, vertices, major and minor axes. These are all things that we'll make reference to later on. Okay. Any questions on that so far? Questions? All right, so let's kind of try to sort out what the form of an ellipse is. It turns out, if you try to encapsulate that geometric property, that the sum of the distances from the foci to any given point is the same number all the time, it's pretty easy to encapsulate using like the distance formula. And basically, if you play that out algebraically, you end up with these equations right here. So first of all, you have like A is the distance from the center to one of the vertices. Okay, so A is the distance from the center to one of the vertices on the major axis. Okay, and by the way, does the major axis have to be oriented horizontally? No, the major axis could be the other way. The foci could actually be vertically oriented. Yeah, and actually, here's the big secret. The foci don't have to be oriented horizontally or vertically. They could actually be like oriented at some kind of other angle as well, right? Some kind of slanted line. And you could actually generate any ellipse you want, but we're just looking at the two cases of being a horizontal major axis or a vertical major axis, okay? And again, 2A is the total length between the vertices on the major axis. Okay, and 2B is the total length across the chord that goes, that kind of is on the ellipse, 2 points on the ellipse through the center on the minor axis. So in other words, going back to this picture, this distance right here is what we call A. Therefore, and this distance right here is what we would call B. And therefore, what would be the distance all the way up and down? 2B. And what about this direction? 2A. Okay. Okay. And I'm going to leave this. Writing on here because I want to grab one other piece of information. Namely, the foci lie on the major axis. C units from the center. The foci lie on the major axis, C units from the center. And the claim is that C squared is equal to A squared minus B squared. Okay, and we'll kind of try to sort that out on the previous picture here. But so look, the claim is the foci lay C units from the center, okay? So here's the center right here. What that is saying is that this right here is C. That distance right there is C. Does that make sense? So the distance from the center to either one of the foci, doesn't matter which one, but that distance is C. And the claim is that C squared is equal to A squared minus B squared. Okay, C squared is equal to A squared minus B squared. Another way to say that is that A squared is equal to what? B squared plus C squared, okay? Now, what does that remind you of? Like I'm trying to sort out why that would be true. What does that remind you of? A squared equals B squared plus C squared. What does that remind you of? Pythagorean theorem. And here's the truth of it, y'all. It is the Pythagorean theorem. And I would challenge you, either while you're watching boats on the lake or eating your lunch at Chick-fil-A or Toast or Chuck's or what have you. If I join the focus up to, oops, oh my goodness, what did I just do? Unbelievable. Let me redraw that, right? So that was supposed to be A right there. Let me draw this in blue. If I go from this focus up to this point, I have a right triangle right here. Do you see that? Yeah? And actually, my claim is that this distance right here is also A. Does that make sense? That distance right there is also A. Why do you think that's true? Okay, let's just kind of think about that together. Then isn't it obvious then that A squared is equal to B squared plus C squared? The Pythagorean theorem would imply that automatically. Why would that blue distance right there, A, be the same as that red distance from the center out to the vertex? this? What do you guys think? It is because of the definition of the ellipse, yes. But what in the definition of the ellipse guarantees that that's going to be true? Help me out here, Maria, or anyone. Right. And what is that constant going to be? Let's kind of think about that. So for instance, let's do something kind of stupid. Suppose I start my string here and I go all the way over to, like, this vertex is on the ellipse, right? So and then this string is going to be anchored right here. Does that make sense? So here is the distance of my string that kind of makes this ellipse. Yeah? How long is that string?
Like you got 2 of the C's and then 2 of that little extra area on the end.
Uh-huh.
And then if you kind of.
So what you're saying is, like, this piece right here, let me use black here. Like this piece right here is the same thing as like this little piece of string right here. Yeah? So the green stuff, so think about it. How far, I mean, and just use one of the letters. I know I heard you say C a couple of times and things like that. But how far is the green string? Think about it. How long is that? 2A. Yeah? So the green string is 2A long. Yeah? But isn't this point right here, let me use some blue here just to kind of drive this home. Isn't this point right here also on the ellipse? Yeah? Okay. So look, but that point, I could stretch a string like this, couldn't I? And what's the length of that string going to be? 2A again, because again, it has to be the same string. You see what I mean? So really, that D1 plus D2 thing, I could describe that in terms of 2A, the total distance across the thing, yes? What's that? Oh, yeah, thank you. Oops. Thank you. Yeah, that should be on the, where should that be? Sorry. Say it again. Yeah, that's what I meant to do. I meant to draw it down to here, right? So the length of that string is 2A total, yes? There's A right here and there's A over there, but it's 2A total, yeah? Because of symmetry, it has to be A here and A here. So that's why this distance is actually A, yeah? And therefore, the Pythagorean theorem gives us that we have A squared equal to B squared plus C squared. Another way to say that is that C squared is equal to A squared minus B squared. So that gives me a way of determining the distance between the center and the focus. Does that make sense? This is geometry, okay? And the Pythagorean theorem in play, and just kind of thinking about the definition of the ellipse. I think that's kind of a neat little exercise, right? Any questions on that? I just wanted us to kind of sort that out together. That's a cool little thing. So again, if we do the math, we end up with these nice little formulas: x minus h squared over a squared, where a is defined, by the major axis. Yeah, it's like the distance between the center and the vertex on the major axis. Okay, and then b is defined as that smaller distance from the center to the point on the ellipse on the minor axis. Yeah. So it's 2b all the way across on the minor axis and 2a all the way across on the major axis. And just to be consistent, we always put the a with the major axis, yes? A is always the bigger of the two, okay? The book does that, so I'm going to do that as well. If the major axis is vertical, A kind of slips underneath the Y thing. Does that make sense? Because A is now the bigger of the two things. But H comma K is the, H comma K is the center of this thing. And again, C is the distance from the center out to the focus, out to one of the foci, okay? Any questions on that? Again, we could show this using the distance formula. It's actually even easier than the parabola to come up with this guy. But I'd rather us spend time on some examples than messing with that too much. Any questions on that? Okay. And this is what I was saying. You can visualize the definition of an ellipse by imagining two thumbtacks placed at the foci, as shown in the figure. If the ends of a fixed length of string are fastened to the thumbtacks and the string is drawn taut with a pencil, the path traced out will be an ellipse. Okay, just kind of neat. I think that's neat. Okay. This is now you can go do that at Chuck's. Okay. Yeah, that's true. You could just, you know. Yeah. Okay. All right. Do this one. Remember, the generic form of an ellipse is x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. Or, right, where a will kind of go either underneath the major, or a always goes with like the major axis, yes? We're always kind of assuming that a is greater than b. So this particular one would be the case where we were horizontally oriented. So this is a horizontal major axis. Okay, so please work on this for a few minutes and see what you come up with. Okay, so work with someone next to you. See what you come up with. You're going to for sure have to do some completion of the square. No doubt about it. Okay. Well, want to talk about this? Okay. So you had to complete the square, right? Yeah, to kind of put it in the proper form. So, so what about this boy? So what about this 4x squared minus 8x thing? Right, so we should probably set that off to the side. 4x squared minus 8x. And then the y squared. Let's do y squared plus 4y. Yeah. Okay. And then let's go, you know, minus 8 equals 0 or something. Yeah. Okay. So, what do we do first here? So like if I wanted to complete the square on this guy that's sitting over here, the x stuff, what would I have to, I mean, look, to me, the first thing you always do is is make the coefficient of x squared 1, okay? So factor that out. 4 times the quantity x squared minus 2x. And then what do you have to add and subtract? Well, we talked about the completion of the square. What do I have to add and subtract to that to make it a perfect square? Yeah, that's right. So then there's a -2 there. You divide that by 2, which is -1, which means I'm going to add and subtract 1 inside of these parentheses. Okay. Now, what about this other part right here? What do I have to do to y squared plus 4y? What do I have to do to y squared plus 4y? Divide 4 by 2, square that, which is 4. So we're going to add and subtract 4. Then I have a -8 equals 0. Yeah? Now how do things factor now? So let me just write the stuff I added and subtracted in red here. So +4 minus 4, which seems stupid, but it's going to be just the trick. Okay? So how do things factor? 4 times what? X minus 1 squared minus 1, yeah? Plus, okay, what about this y stuff? Y what? Y plus 2 squared minus 4 minus 8 equals 0. Okay, let's mess with this a little bit. If I distribute the 4, okay, and combine constants and whatnot, I'm going to end up with 4 times the quantity x minus 1 squared plus y plus 2 quantity squared minus 4 minus 8 is, that's 16. So would you guys object to me moving that negative 16 to the other side? Okay. But of course, take a peek at this. This thing always has a 1 on the other side, yeah? So what should I divide through by? 16, right? So if I divide by 16, I'm going to end up with x minus 1 squared over 4, which maybe I should write that as 2 squared. You know what I mean? And if I divide the second thing by 16, isn't that like, let me write this as y minus, why would I write it as y minus negative 2 again? Because, because the form of the thing is x minus the center and y minus the center, yes? But what would be down below the y minus negative 2 quantity squared? 4 squared. Okay, so that's equal to 1. Now, okay, that's interesting because what that means is, what's the major, okay, so like what's A and what's B? A is 4, B is 2. Oops, what am I writing? B is B, of course it is. Yes, B is 2. So what is C? Remember, C squared is equal to A squared minus B squared. So which, by the way, is 16 minus 4, which is 12. And if I take the square root of that, I get C equal to, what is it? Is that like 2 root 3 or something? Yeah? Now remember, C is supposed to be, 4 is the distance from the center to the vertex on the major axis, yes? That's what 4 is. What about C? Yes. Well, no, A is always the bigger of the two. Right, remember? I mean, you can't really see that right there, but B is always, or A is always the bigger of the two. So what's going on here? What's the major axis in this case? The major axis is what? Is it horizontal? No, it's vertical. Here we have a vertical major axis. That makes sense? Yeah. Okay, so let's kind of think this through. We're going to have a vertical major axis. The distance from the center, by the way, what is the center here? HK 1, negative 2. Okay, that is the center. The distance from the center to the vertex is 4 units, and I'm going to move vertically to do that, yeah? And the distance from the center to the foci in either direction is 2 square root of 3. Make sense? 2 square root of 3. That is bigger than 2, but less than 4. Because like square root of 3 is like 1.7 something, 2 times 1.7 something, I mean, it's like 3.4, somewhere between 3 and 4, yeah? So it's smaller than 4, which makes sense because the distance from the center to the focus should be smaller than from the center all the way to the vertex, yes? That should be a smaller distance. Okay, so here is all the major information that we need sitting right here. Okay, that information right there is enough to tell me precisely what the graph of this thing has to look like. Does that make sense? Okay. In fact, we could kind of try to sketch that thing here. I think I've actually put everything on the next slide here. The entire, oops, yeah. There's all this. There was all the computation right there, and then I actually graphed this thing, okay? So I'm going to clear this off at this point because all of that information is in there, okay? So the center is 1, -2, okay? Here's the formula that we came up with. The center is 1, -2. The vertices I get by moving 4 units in the vertical direction either way, because A was 4, okay? As you can see, I said H is 1, K is -2, right? H and K are the X and Y coordinates of the center. B is 2. So to get to the vertices, I go from 1, -2, and I subtract 4 to go to the bottom vertex. I add 4 to go to the top vertex, okay? And then how do I get to the foci? Well, I go to the center and I add and subtract 2 times the square root of 3, yes? And so this is the picture of what you get when you do that. Cool, does that make sense? This is a picture of everything that's happening with this, okay? There it is, yeah. There's also a reflective property of an ellipse. Remember last time we talked about like that there's a reflective property of parabolas that give it some nice features that you can take advantage of. If P is a point on the ellipse, okay, so let me just kind of draw a generic ellipse here. This is not an accurate rendering, okay? But if you take a point P on an ellipse, okay, so here's point P, okay? And I draw the tangent line to the ellipse at this point. Okay, so there's the tangent line. Okay. The tangent line makes equal angles with the lines through P at the foci. Okay, so if I draw this and this, then what's true about this angle right here? What's true about this angle right here? It's going to be the same as this angle right here. Does that make sense? Okay, so there's still this kind of reflective property thing going on in this case as well, okay, which is kind of neat to think about. Okay, all right. And I said here, one of the reasons astronomers had difficulty detecting that the orbits of the planets are ellipses is that the foci of the planetary orbits are actually really close to each other. Right? And if the foci are really close to each other, what are you almost going to be drawing? Think about it. It's almost going to be a circle, yes? In fact, it's when the foci converge into a single point that we get a circle. So if A is equal to B, that actually is the equation of a circle, is it not? You think about it. I go back to this equation right here. If A and B were equal, so if A and B were both like r squared and r squared, then I can multiply through by r squared and I would get x minus h squared plus y minus k squared equals r squared, which is the equation of a circle, yeah? Because this is describing, basically, if I take the square root of this, so that this power went away, this is describing the set of all points, x, y, that are at distance r from the center h comma k, yes? Because this is the formula for distance between a point, between x, y, and hk. This formula says distance between x, y, and hk. If you think about it for a second, that's saying that that's constant. So if A is equal to B, we get a circle. So A equal to B implies that we get a circle, okay? So that's one special situation that's rolled into the ellipse one, okay? All right. So the measure of the ovalness of an ellipse, to measure the ovalness of an ellipse, you can use the concept of eccentricity. Eccentricity, okay? So eccentric means it's really, the more eccentric it is, the more squatty it is, the more squashed down the thing is, okay? So remember, c squared is equal to a squared minus b squared, right? If A and B are equal, so think about it. If A was equal to B, what would C be equal to? 0. And so what would the eccentricity be in that case? 0. There would be no eccentricity. So this situation describes the circle situation. Yeah? So the more eccentric you are, the more squatty of an ellipse you actually have. Like it measures the ovalness of it. Yeah? That means the foci are getting really far apart. Does that make sense? The foci are getting really far apart, and B is getting small and relative to A. Okay? But C is always smaller than A, because C is the distance from the center to the focus, and A is the distance from the center all the way out to the vertex on the major axis. Okay? So eccentricity is measured by C over A. Yeah, so right. This number right here, so let's just look at this picture to see how this ratio is used to describe the shape of an ellipse. Note that because the foci of an ellipse are located along the major axis between the vertices and the center, it follows that C is between 0 and A. That's basically what I was already saying, yes? C is smaller than A, and positive, of course. So if the foci are really close, then that distance right there from the center to the focus is smallish, yeah? So C over A would be small. But the further out the foci goes, actually the distance, the length C and the length A become closer and closer to one another. Does that make sense? Okay. So in the limit, you're going to get something that's closer to 1. C over A is closer to 1. The eccentricity is higher. So the eccentricity number is always a number between 0 and 1, right? If the eccentricity is 0, what do we have? A circle. If the eccentricity is really close to 1, what do we have? You have a really squatty looking ellipse. Does that make sense? A really, really dramatic oval looking ellipse. Okay? That's interesting. For an ellipse that is nearly circular, the foci are close to the center and the ratio is small. For an elongated ellipse, the foci are close to the vertices and the ratio is close to 1, as we just saw in that previous figure. And the eccentricity is always trapped between 0 and 1, as we just said. Yeah? Here's some actual numbers from planetary orbits. Okay? Again, the eccentricity is unitless quantity because you divide a length by a length, right? So it's a unitless quantity. So it's going to be, right? These numbers have meaning even when we're talking about planetary orbits. So the eccentricity of Mercury, the Mercury orbit around the sun is 0.2. But man, look at some of these. Look at Venus. The eccentricity is almost 0. You see that? It's amazing. So it's almost a circular orbit, yeah? Same with some of these other ones. Earth's pretty close to a circular orbit as well. And Mercury is the one that kind of has a more elliptical oval type orbit. That's sort of interesting, I think, right? I just kind of pulled that, for you to think about, for sure. Okay. It turns out, by the way, what's the formula for the area of a circle? So for a circle, what is the formula for area? Area is equal to pi r squared, which, by the way, is pi times r times r. Do you know what I'm saying? Yeah? It turns out that the general formula for the area of ellipse is pi times a times b. Yeah? And when you're in the case of a circle, A is right here and B is right here. It turns out that you can use integration to actually establish that formula, which is kind of interesting. Yeah, so it's pi times the major axis length times the minor axis length, and then you'll have that thing. Yes, there is a formula for the circumference as well. I was going to show you, in fact, I mentioned that right here. So here's like just how you would actually prove the formula for the area of an ellipse. You would actually integrate, like you would solve for the equation of the upper part of the ellipse. You would integrate that thing, and guess what you would have to use? A trig Substitution. And look, do you have a cosine squared right there at some point? What am I going to have to use at that point? Do you remember? Half angle identity, yeah? And then you would do it, and I'm telling you in the end, if you kind of follow your nose on this, you would get pi times A times B. To find the formula for the circumference of an ellipse, it's not so simple, but I really want to challenge you to go think about that. Okay? There is a formula for that, but it's not quite as simple. Of course, the formula for the circumference of a circle is trivial, isn't it? What is it? 2 times pi times the radius, yes? Or pi times the diameter, if you will. Formula for the circumference of an ellipse is not so simple, but you can try to go think about that if you were so inclined. We'll actually have tools to do that more readily pretty soon, actually, though, okay? All right, I'm gonna leave it at that, and we will talk about hyperbolas next time.